Okay, so this video is going to provide the solutions to the connecting force and kinematics problem that I gave you guys on Monday. So to start out with, this problem says, consider two blocks. The first has a mass of m, the second has a mass of 2m. Both are at rest on a frictionless table. At time t is equal to 0, force given by f of t vector is equal to minus beta t plus gamma times quantity times x hat is applied to each block where m, b, and gamma are all known constants. Use dimensional analysis to determine the units of beta and gamma. Okay? So in order to use our dimensional analysis here, we know that force has units of newtons, which is the same thing as a kilogram meter per second squared. And so whatever I have on the left side of the equation needs to have units of newtons. Whatever I have on the right side of the equation needs to have units of newtons. This says that units of beta t also need to be kilogram. This is a kilogram meter per second squared. And so that says that beta has units of kilograms meters per second cubed. And gamma is not multiplied by anything. So gamma just has units of newtons itself. So this is going to be kilogram meter per second squared. Okay? So for part B, we want to draw the free body diagrams for these. So this is going to be my mass m. This is going to be my mass 2m. So pretend that this actually is twice the size. But when we draw a free body diagram, we have some normal force. We have some mg, and we have the force that we're applying here. So this is going to be our F. Let's call it F. Okay. Same thing with our N, our M2. So this is going to be 2mg, and this is going to be F. Okay. So there's no friction here, just the applied force, the normal force, and the gravitational force. Okay. So the next thing that we want to do, so for C, now that we have our free body diagrams, we want to determine what the normal force is for each object. And so let's go ahead and define a coordinate system for these. So I'm going to call this the plus x direction. I'm going to call this the plus y direction. Okay. So then when we're determining what the normal force is, we're just summing our forces in the y direction. So you can sum our forces in the y direction. So sum of forces in y is going to be equal to m-a-y in general. But these are constrained to stay on the table, and so the acceleration in the y direction is 0. So for the first block, that says that n minus mg is equal to 0. For the second block, that says n is equal to n is going to be equal to 2mg. Oh, sorry. N minus 2mg is equal to 0. And let's give these some subscripts to denote that they're different. And so this says that n1 is equal to mg, n2 is equal to 2mg. Okay. Now it might seem like I went through a bunch of extra steps in order to do this. Why not just say that n is equal to mg? And that's because it's not true in general. So you always want to go through this process exactly the way that I'm doing it here, because as I like to tell you guys, I would like to give you the things that are always true. This process is always true. Saying that the normal force is equal to the gravitational force is not always true. In fact, most of the time it's not true. Okay, so that's part C. The next part that we want to do is we want to apply Newton's second law to find the acceleration for each block. And so to find the acceleration in the blocks is just considering what's happening in the x direction. So this is the sum of the forces in the x direction is going to be equal to max. So for the first block, what this says is that the sum of the forces, which is just the force that I'm applying, is going to be equal to the mass times acceleration. So this is minus beta t plus gamma is going to be equal to the mass times the acceleration in the x direction as a function of time. Okay. So that's for our first block. For our second block, really we're applying the same force. So this is going to be the same minus beta t plus gamma is going to be equal to, now this is going to be 2m times a. And let's make these very explicit. So this is going to be a1 sub x And actually, there's only an acceleration in the x direction, so what I'm going to do is I'm just going to suppress the index for x, right? If we had accelerations in y, maybe it might be worth writing that, but I'm just going to ignore it here. So this is what we have, right? So now we can algebraically rearrange these equations to find what these accelerations actually are. And so a1 of t is going to be equal to 1 over m times minus beta t plus gamma, and a2 of t is going to be equal to 1 over 2m times minus beta t plus gamma. And so ultimately what we're seeing here, this second block has twice the mass. Well, we're applying the same force to these, and so really a2 is just going to be equal to 1/2 a1 of t. Okay. So this is what we have right here. Okay. So the next thing that we want to do is we want to determine what the velocity and the position as a function of time is for each block. So let's just look at our block 1. So a1. We know the relationship between the velocity and the acceleration is such that dv1 dt is equal to a1 of t. So we can determine the velocity as a function of time by multiply both sides by dt. And we can integrate. And so this says that v1 of t is going to be equal to the integral of 1 over m minus beta t plus gamma dt. Do our integral here. This is going to be 1 over m times minus beta t squared over 2 plus gamma times t plus a constant of integration. So here's our v1 of t. So v1 of t is going to be this. And so ultimately what we want to do here is we want to say that our initial velocity is going to be 0. These both start from rest. And so that says that v1 of t is equal to 0 is equal to 0, which says that c is equal to 0. And so v1 of t is going to be equal to 1 over m times minus beta t squared over 2 plus gamma times t. Now we can find what our position as a function of time is going to be. So our position as a function of time, x, is going to be related to the velocity via dx1 dt is equal to v1 of t. Multiply both sides by dt. Integrate. It says that x1 of t is going to be equal to the integral of what we have here, 1 over m minus beta t squared over 2 plus gamma times t times dt. We do this integral. This is going to be 1 over m times minus beta t cubed over 6 plus gamma t squared over 2 plus new constant integration. Okay, so there's our x1 of t. And what we're going to do is we're going to choose our coordinate system such that the position is 0 at time t is equal to 0. So that's to say that x1 of t is equal to 0, is equal to 0, is equal to c. x1 of t is equal to 1 over m minus beta t cubed over 6 plus gamma t squared over 2. And this is our position as a function of time for our first block. Now, what we can do in order to find our position versus time and our velocity versus time for our second block is just to go back to this relationship that I have here. Right? So the acceleration for 2 is just going to be half the acceleration of 1. And so when I'm doing this, you can go through the entire process yourself. Really, this ends up carrying a factor of 2 through the entire thing. And so what this is going to say is that v2 of t is going to be equal to 1 over 2m times minus beta t squared over 2 plus gamma times t. And x2 of t is equal to 1 over 2m times, this is going to be minus beta t cubed over 6 plus gamma t squared divided by 2. Okay? So these are our equations. Okay? So if you don't trust that calculation that I did, I didn't actually do the calculation. I argued why you didn't have to do the calculation because it's just scaled by a constant in front. But if you don't trust the calculation, go through it yourself. Make sure that you believe that calculation. Okay, so the next thing that we want to do is we want to determine how long it takes for each of the blocks to turn around. So why are these turning around? It's because the force that I'm applying to this is changing, and then at some point it changes direction entirely. So that means, as always, when we're talking about whether something turns around or not, this is going to be to say that the velocity as a function of time, and we'll just look at the first one. So v of t is equal to some special time. I call this t m max, I believe is the way I define this here. Yep, or max of m. It doesn't matter. I'm just interchanging the order of my subscripts. So this is going to be equal to 0. And so we can take that function. We have this is equal to 1 over m times minus beta t squared over 2 plus gamma times t. And these are going to be m comma maxes, m comma maxes. And so what we can see here is that we have one what's called a trivial solution. That's when t is equal to 0, but the interesting solution occurs later on. So I'm going to just cancel one of these masses, and so this is going to be just to the first power now. And so the non-trivial solution occurs when t m comma max is going to be equal to gamma, or 2 times gamma, divided by beta. Okay? And you could check this for dimensional analysis to make sure that this is dimensionally correct, and we have this factor of 2. So this checks out. Okay? Now we can do the same thing for our second mass, and we're going to see something rather interesting here. This is going to be v2 of t is equal to t2m comma max is equal to 0 is equal to 1 over 2m times minus beta tm max divided by 2 squared, and this is our 2m, plus gamma t 2m comma max. Again, we can solve for this, and what we're seeing actually is that these two times are the same. It takes the same amount of time for these to turn around. So that seems kind of strange. So what gives? We're going to see exactly what gives in just a second. And so t 2m comma max is also going to be 2 gamma over beta. Okay. Now, here is the interesting part. Okay. This is going to come when I'm trying to find how far each one of these actually goes when these turn around. Okay. So f, this is going to be g. So now that we have these times, and I'm just going to consolidate this and call this t max is equal to 2 gamma divided by beta because they're going to be the same distance, or sorry, the same times. We just need to evaluate these functions. So this is going to be x1 of t is equal to t max. This is going to be equal to 1 over m times minus beta times t cubed over 6 plus gamma times t squared over 2. And these are evaluated our max times. Okay, so let's go ahead and take these and plug them in. So this is going to be 1 over m times minus, this is going to be beta over 6 times 2 gamma over beta to the third plus gamma times 2 gamma over beta squared. Okay, so let's reduce this a little bit. So this is going to be equal to 1 over m. I'm just going to get this minus beta over 6. We have a beta cubed in the denominator. Beta cubed, we're going to have a 2 cubed, which is 8. and then we have a gamma cubed. Gamma cubed, okay? Now the next part here, this is going to be plus gamma times, this is going to be gamma cubed ultimately, so this is going to be gamma cubed, 1 over beta squared times 4. So let's reduce this a little bit. So this is going to cancel a beta here, so that's going to give me a beta squared in the denominator. This 8 and this 6 can be reduced, so this is going to be a 4 over 3. And so let's collect some things and write them in a similar fashion. So this is going to be 1 over m times 4 over 3 with a negative sign times a gamma cubed over beta squared plus 4 gamma cubed over beta squared. Now, in order to combine these, we need a common denominator. This is going to be a 3 over 3 to multiply this to get a common denominator. This is going to be 12 minus 4. So this is going to be 8 thirds. So this is going to be equal to 8 over 3 times gamma cubed over m times beta squared. Okay? So let's go back through and check our dimensional analysis here. So we know that gamma is going to be units of newtons. So we have a newton. Beta is going to be in units of newtons per second. So this is going to be newtons cubed, newtons per second. This is going to be squared. And so we also have a mass here. So this is 1 over mass. So we have units of newtons per mass per second. Let's write out what a newton, so let's not write this as an m, let's write this as a kilogram. So this is going to be a kg per second. And so this is going to be kilograms meters per second squared. This is a second squared. That's a second squared. And so what we're going to see here is that ultimately, so this is going to be kilogram per second squared. Sorry, I'm jumping around a little bit too much. So this is a second squared. This is a kilogram meter per second squared divided by a kilogram per second squared. That's what we're looking for. And so our kilograms are going to cancel, our second squareds are going to cancel, we're left with units of meters. So at least dimensionally, this is correct. And barring any little mistakes in our arithmetic here, this is also correct. Okay, so this is our x1 of t is equal to t max. Now, we could repeat this entire calculation for x2, but again, we note that the real difference between x2 and x1 is just this factor of 2. And so what this says is that x2 of t is going to be equal to x1 of t divided by 2. And so when I evaluate this, really, I'm just going to find that it's going to be half the distance. x1 of t is equal to t max. So it's going to be half the distance. This is going to be 4 thirds gamma cubed over m beta squared. Okay? So those are our distances. So I'm going to come back in a second to plot these so that I can actually do it in Mathematica. So we have really nice looking plots. Okay, I'll be back in a second. Okay, so I've made my plots, and actually in the time that I was doing that, I went back and I looked at my work, and I saw I was missing a factor of 2. So those of you that are keeping score of the factors of 2 and negative signs that I leave off, score point for you guys because there was one missing here. But just as a general comment, the dimensional analysis is a very useful tool for checking a lot of things, but you're never going to be able to catch negative signs and factors of 2 and 5 and so on. So you have to, even if you're using dimensional analysis, that's only but one tool to check your work. And ultimately, the way that I found this was in making the plots, they weren't agreeing with the answers that I got, and so that made me go back and check, and it actually was a factor of 2 that I dropped from this line, going from here down to here. Okay, so just try to keep those in mind. And again, this is why it's important to be recording your thought process, because I could find exactly what line I lost the factor of 2 because I've recorded everything here, and I could see exactly where I needed to insert the factor of 2 and then where I need to carry it through. Okay, but that's enough ranting for me. Let's take a look at the plots that we have here. So the blue line is the line for the mass that has twice the mass of the other one. And the orange or yellow line is the one that has the unit mass, the mass of 1 here. Okay, so let's kind of talk through our plots here. And so we can see that when we started from the force, so the force was going to be equal to, force is a function of time in the x direction, was going to be equal to minus beta t plus gamma. Okay, and so when I plotted this, I assumed beta was 1 and gamma was 1. In addition, m was 1. And so what you see here is that when you have the acceleration 2, which is the one that corresponds to this one, this is going to ultimately end up being equal to f of t divided by 2, and a1 of t is going to be equal to f of t divided by 1, essentially, because I'm also assuming a mass of 1 for both of these. And so you can see that when you're looking at this, that this really does tell the story here, because the blue line has a shallower slope and it has a smaller intercept. And that's effectively what would happen if you took this f of t and you divide it by 2. Okay, so there's a point that's kind of interesting here on this plot. This point is the point right here. This is the point where the acceleration changes direction. So you're pushing this along, and this is when the force is actually going to start pointing the other direction. The objects are still going to be moving, but this force is now going to be slowing it down instead of speeding it up. Okay, so then we can look at our velocity plots, and again we see the same thing here, that the velocity is at a maximum when the acceleration changes direction. And again, that kind of makes sense because I've been pushing it to speed it up this entire time, and then I'm turning my force around and I'm going to be slowing it down. And so the velocity is going to be the largest like at the instant that I start turning around the direction of the acceleration. Okay. And then also what's interesting with this acceleration, this velocity plot for these two, is that the time that it takes, the time that we solve for in this part F, the time that it takes for these to reach their maximum is going to be when the velocity is 0. And we see from these plots that that's actually going to be the same time. Okay, so that's where our Tmax is for the values that I chose here. This is going to be 2 seconds. And then we can see our position plots for how far these things are going to go in those 2 seconds. And so again, we can see that from our position plot, this is got a slope of 0. This has got a slope of 0. This is where our objects, our masses are going to be, where they've gone the furthest that they're going to go. And this occurs at this time 2 seconds. So t is equal to 2 seconds is when they've gone the furthest that they will. And we see that the mass, so this, remind you again that this orange or this yellow line is the mass m. This is the mass 2m, okay? So the mass 2m isn't going to go as far as the mass m. But the thing that's kind of interesting about this is that it takes the same amount of time for these to reach their maximum distance, okay? So that was kind of the interesting takeaway from this. And then the other thing that we could do here, if we wanted to, we could draw a line going all the way down from our acceleration plot here. And this is what's called an inflection point that we can see on our position plots. This is when the concavity of the position plot changes, and that's when the acceleration is changing. You can actually see that on the position plot. Okay, so that's going to be it for this video. I hope that's going to be helpful for you guys. If you have any questions about this, let me know, and otherwise, take it easy.